The objective of the Marshall stability test is to determine the optimal bitumen content in the bituminous mix that provide the best combination of stability, flow, and volumetric property for flexible pavement construction. Especially, the test aims to first evaluate the maximum load carrying capacity, Marshall stability of the bituminous mix. Second, measure the deformation flow value of the mix under loading conditions. Third, assess the effect of varying bitumen content on the strength and flexibility of the asphalt mixture. Fourth, determine the optimal bitumen content OBC that meets the required specification for pavement performance. Fifth, ensure that the mix design has adequate durability, density, and resistance to deformation and cracking under traffic loads.
I will explain the theory behind the Marshall stability test. The Marshall stability test is a standard lab procedure used to design and evaluate bituminous mixes for flexible pavement. It was developed by Bruce Marshall in the 1930s. This method is popular because it's simple and effective in improving the strength and durability of asphalt mixtures under traffic loads. The test mainly checked two things. First, the stability or the load-bearing capacity. Second, the flow or how much the mixture deforms under pressure. In this test, we prepare cylindrical specimens, usually 101.6 mm in diameter and 63.5 mm in height. These specimens are made by mixing heated aggregates with different percentage of bitumen, usually between 4% and 6%. Then, we compact the mixture using 75 blows per phase with a hammer, especially for heavy traffic use. After that, the specimens are placed in a water bath at 60 degrees Celsius for 30 to 40 minutes to stimulate the real field condition. Finally, we place the specimen in a Marshall testing machine. This machine applies a compressive load at a constant rate of 50.8 mm per minute until the specimen fails. They have two key values are recorded during the test. First, Marshall stability, the maximum load in kilonewtons the specimen can sustain before breaking. Second, flow value, the total deformation in millimeters of the specimen at the point of maximum load. In addition to these two parameters, volumetric properties such as air voids, voids in mineral aggregate, and voids filled with bitumen are calculated to ensure the mix has proper density, durability, and resistance to deformation or cracking. The optimum bitumen content is selected based on the mix that provides maximum stability, acceptable flow usually 2 to 4 mm, air voids in the range of 3 to 5%, adequate VMA typically greater than 30%, and VFB 65 to 75%. A mix with insufficient bitumen may be strong but brittle, while excess bitumen can cause deformation or rotting. Thus, the Marshall method balances both stiffness and flexibility of the pavement.
Okay, next, I will present about sample table, bitumen content versus stability and flow. So this table illustrates how stability increases with bitumen content up to a constant point, usually around 5.0%, after which it begins to decrease while flow continues to rise. The optimum bitumen content is typically selected at the peak stability value with acceptable flow and void parameters. Tools used in Marshall stability test is first balance sensitivity to 0.5 gram, next Marshall mold, 4 inch diameter and 2.5 inch head. Next, compaction hammer, weighting 4.5 kg, 457 mm drop. Next, water bath, maintains to 60 degrees Celsius. Next is oven for heating mix. Next, loading machine with proving ring and dial gauge. Next is stability and flow meter. Flow meter is 4 inch diameter and 2.5 inch head. Next, last is bitumen and aggregate, 4 inch diameter and 2.5 inch height.
Procedure. For bulk mixture preparation, measure the amount of aggregate and filler to be used in order to meet the specification limit. About 1,200 grams of blended aggregate, sand and filler, is prepared in a container to produce a Marshall specimen. Oven dry the aggregate at 150 degrees Celsius for at least 4 hours. Heat the asphalt at the same temperature, or at mixing temperature, which is about 140 degrees Celsius. Place the heated aggregate into the mixer, and blend dry for 1 to 2 minutes. Add appropriate amount of asphalt, based on the percentage of total mix weight, and continue the mixing process. Before compaction, ensure the ready bulk mix temperature for compaction is equal, or more than 137 degrees Celsius. The mold, scoop and spatula must be preheated as well. Use the scoop to transfer the asphalt mix into the mold. Next, use the heated spatula to rod the mix vigorously 15 times around the perimeter of the mold, and 5 times over the interior. This process ensures a smoother specimen, and eliminate any bridging of the rock. Compact the mix carefully using the Marshall compactor, for the proper number of blows as specified in the mix design. Reverse and reassemble the ball, and apply the same number of blows to the face of the reversed asphalt mix. Use an extruder to remove each specimen by jacking the specimen up through the hole, keeping the specimen as perpendicular as possible, so that the specimen is not distorted. Measure the specimen height, and weight in air and water. Determine the specimen density. Heat the specimens in a water bath, to a temperature of 60 degrees Celsius, for 30 to 40 minutes. Place the specimen in the Marshall testing rig. Load the specimen ratially at a constant rate of strain of 50.8 millimeters per minute. A trace relating strength and deformation is automatically recorded on a graph paper. Determine the stability of each specimen as the maximum load that the specimen could withstand. Apply correction to the stability values if required. Read also the deformation at failure and report this value as the flow in millimeter. Thank you for your time.
Okay, next, this is data and calculation.
Okay, for data and calculation, stability and flow value determination. So mixing temperature is about 149 degrees Celsius to 155 degrees Celsius. Number of blows on either side is 75. Grade of bitumen is VG40. Compaction temperature is 95 degrees Celsius to 150 degrees Celsius. Proving ring calibration factor is 0.307. Flow value dial 1 division is 0.01. Okay, as you can see, this is our observation table for density and voids. So we have specimen number, bitumen content, height of specimen, weight of specimen in air, weight of specimen in water, weight of specimen in SSD, bulk volume, and bulk density. So next, we have observation table for Marshall stability and flow value. We have specimen number, bitumen content, Marshall stability, that is shown by measure load, thickness correction factor, proving ring correction factor, corrector load, and lastly, flow dial reading. Okay, next is optimum bitumen content determination. B1 equals to bitumen content corresponding to maximum density, that is 10%. B2 equals to bitumen content corresponding to maximum stability, also 10%. In addition to this graph plotted between with bitumen content on x-axis and equal to bitumen content versus Marshall stability and bitumen content versus density graph. Okay, lastly, bitumen content versus flow. Result is optimum bitumen content equals to 10%. Marshall stability at optimum bitumen content is 271.68 kg. Marshall flow value at optimum bitumen content equals to 1.9 mm. In conclusion, the Marshall stability test successfully determined the optimum bitumen content for the bituminous mix by analyzing the relationship between bitumen content, stability, and flow value. From the test result, it was observed that stability increased with bitumen content up to a certain point and then began to decrease, while flow value consistently increased. The optimum bitumen content was selected based on the peak stability value combined with acceptable flow and satisfactory volumetric properties such as air void VA, voids in mineral aggregate VMA, and void filled with bitumen VFB. The test confirmed that a well-balanced bitumen aggregate meets ensure adequate strength, durability, and resistance to deformation under traffic loads. Therefore, the Marshall methods provide a reliable and empirical approach for designing bituminous pavement that can withstand expected field conditions.